right, so we're moving on. Moving on to more hybridization. We're going to talk about double and triple bonds. That's when it gets a little more difficult. I'm going to take you through 2 different examples where we do the whole kit and caboodle of how to organize this. Now, did I do this with you already, SP3D? No. All right, so let's talk about these. This is not double or triple bond. These are still octet violators. So I tried to give you a sheet that summarized some of our octet violators and some of the more important things that we talked about in the lessons over the past couple of days. So that sheet that you guys all picked up. Oh, you didn't pick up the sheet?
I got it.
Oh, you got it? Okay. So I'm hoping that it will summarize a little bit more all the details, all the little things that we touched on. All right, so moving on to another octet violator, we've got PF5. Right away when you see this, and you'll notice that every single one of my slides does this because this is what I expect you to do. The starting point is I give you a molecule. And you're going to create your Lewis dot diagram or whatever it is. When you're looking at this, you say, no, this doesn't look like. Phosphorus can be an octet violator. It starts to utilize its d orbital in order to achieve this type of molecule. Molecular compounds, PF5, SF6, Cl2O, all of those, they will do things or move their electrons around so that sharing is maximized. So when we have PF5, the first thing you do, okay, it's an octet violator. So the most likely structure is this. So which means that phosphorus can form 5 covalent bonds. It can do that because you've got your d orbital available for it. Now what is the structure going to look like? Well, it looks like this. It's a trigonal bipyramidal. So it actually, in all honesty, it looks like a seesaw with these fluorines going up and down, teeter-totter. Right? You don't know this yet. You will learn them at the end of the meeting, what they actually look like. But when we move forward, what does it look like? Well, what you need to do is you look at the energy level diagrams and you create your hybrid orbitals, trying to figure out how does PF5 actually form a stable compound. Well, this is what your energy level diagram is for phosphorus. Like I said before, when you do this, you do not need to do the 1s, 2s. You don't need to do the kernel of the atom. It doesn't make any impact. It's the 3s and 3p. So how is it that phosphorus is able to do 5 covalent bonds? It excites its electrons and moves it in. So what ends up happening is 1, 2, 3, 4, 5. What do we call this hybrid orbital? Well, sp3d. So your new hybrid orbital is sp3d. You've got 5 of them, and that's where you go from there. Okay, so this hybrid orbital, now you have to remember, each one of these, they are no longer on a hierarchy. Okay, please keep that in mind. It's a common mistake that grade 12s, even university students do, is that they think that that last one is the first one that has to be filled. No. They level their playing fields, which means that all 5 of these are equal. So it doesn't matter which one got filled. We just happen to do it in order. So what does the structure look like? Well, we say phosphorus is said to be sp3d hybridized. You'll notice that all the hybrid orbitals are usually little teardrop shapes or long ovals. That's what we always get. Okay? Now, if you were going to do this and bond it with fluorine, you're going to see this, the hybrid orbitals. Now, if you're doing this, what is the orbital that all halogens, specifically in this case fluorine, what orbital does it have available for overlap? The p orbital. So you're going to call this one. This overlap is a P-SP3D orbital. This one. 1, 2, 3.
SP3D-P.
Exactly. All right. This one. 1, 2, 3.
SP3D-P.
Very good. All right, so we're always moving. It's the top left, gravity moves to the bottom right. So all these types of overlaps, what type of bond are they? If it's a direct overlap, we call them
Sigma.
sigma. All right, we no longer call them single covalents. They're sigma bonds. Direct overlaps are sigma bonds. All right, so this is, and then once you combine them, then you end up with this final structure that looks like this. So that's your sp3d hybrids. You don't have a lot of those kind of molecules. But if you happen to draw that one on your quiz, then you're gonna have to know how to do an sp3d hybrid. Now, if you're really unlucky, you might end up getting an sp3d2. Okay? And once you see this, sorry, this is supposed to be SF6. I don't know why it didn't show up. All right, so you have SF6 here. And you're saying, once again, okay, sulfur is forming 6 covalent bonds. And you're thinking, okay, well, it's a little bit more difficult to do in that particular case. You draw your Lewis dot diagram. You know it's an octet violator. It doesn't follow the same things that it normally does. But then you have your octahedral. Okay? Now, what is it going to look like? Well, you always take your most central atom, and you've got your sulfur. This is what it looks like. 3s, 3p, and this is what it would do. What you have to do is figure out, once you've drawn your Lewis dot structure, you know you have to figure out how is sulfur going to create its hybrids to do this. The issue is, if you don't draw your Lewis structure properly, then all else fails. So that's why we spent the time, you have to know how to draw your Lewis structures. So in this particular case, as you can see, how does sulfur produce that 6 bonding sites? Well, it just forces 2 of them up into the d orbitals. So what it had here, the one here and the one here, it's hybridized. So then we have the sp3 and then d2. Okay? So this is another octet violator where you have sp3, d2. Lucky for you, that's as far as I'm going to make you go. Okay? Because you can have hybrid orbitals of F's. With F orbitals. But for your sake, we're only going to go to sp3d2. Yes, Cole?
So for these SPD or hybrids, the shape would be different because of the shape of the D, but for now we're just going to use the droplet shape. Okay.
Exactly. Yes, Lucy.
Can you ever have hybrids without an
Unlikely, because that's where electrons are being excited from. So you have to include the S all the time. Okay? Depends on how you're going to rearrange. But this is the highest one we're going to do, sp3d2. And most of the time, that's all you ever will go to. There's no sense in going. There's the other hybrids. You never talk about them because you'll never get to that point. All right. So this is sp3d2 hybridized. And once again, when you look at the actual molecules of SF6, all we do is just do it this way. Yes, Lucy?
Are all of these on the same plane?
No. No. Right now, we're just doing baby steps. So right now, we're just doing 2-dimensional. Once we have all this down pat, after you've written the quiz on it, and then I make sure that everybody knows how to do hybrid orbitals, then we introduce this.
When is the quiz?
When you guys tell me you're ready.
End of the semester.
Sorry, Mitchell?
End of the semester.
Yes. No, it's gonna be sooner. All right, so anyways, and then in this particular case, the same thing. This is what is this overlap gonna be called? 1, 2, 3.
Yep.
SP3D2-B.
Okay, good. sp3d2-b, in your own way, sort of said it. All right. This one. 1, 2, 3.
SP3D2.
Good. All right. So you have to be able to label. You have to label each and every one of them. Okay. So that's what you end up doing. So we have a whole bunch of different molecules here. It's fine, you can do that, but that's why I created that worksheet for you. You're going to be doing all of them, but we only did sp3d2. We haven't talked about double bonds or triple bonds yet. Yes, Cole?
So for the hybrids, the P would have the double, but also on both sides.
Yes.
So one is to include the smaller double on the opposite opposite side of our orbital.
Okay, I'm gonna show you, what we're gonna do. So, when you're doing these, in the summary, you have to remember the shape of the molecule you create with your Lewis structure. This is very important, all right? Is it linear? Then it's SP. If it's trigonal planar, then you have to create your SP2. Is it tetrahedral? SP3, and so on, all right? Depending on your Lewis structure. So please, if you're gonna spend any time, you make sure your Lewis structure is perfect. It must be. All right, so. So let's put this into practice, where we're gonna do the double bonds and triple bonds.
Just like plug it. Okay.
She's on this because I don't like to close stuff. All right, are we good? Now, this is where the fun begins. Thanks, Kyle.
I thought we were already in the fun.
No, this is,
Oh.
okay. Now, on your sheet, then I'm going to introduce a new bond. You've done sigma. These are pi bonds, okay? And it's actually written the same way as 3.145. All right, we call these pi bonds, and this is on that very first sheet when we have an indirect overlap. Okay? Indirect overlap means that it's going to be a pi bond. Sort of like Jasmine and Melissa, all right? And they're doing something, and then Jasmine puts her calculator here. Melissa forgets hers, but they're such good friends that Melissa, when she needs to calculate something, she just grabs it, right? She doesn't have to ask Jasmine. It's sort of an unwritten rule that it's sort of there. You can just share it. It's okay, all right? It didn't matter. And the same thing happens with pi bonds. It's sort of in the vicinity that you can use it, but it's not really yours, but it satisfies the 2-electron rule to make a bond. Okay? Now, how does this work? Well, let's looking at C2H4. What's that molecule? It is, what is this molecule? C2H4. Come on, you guys. Methene, right? C2H4. Seriously. You guys. Okay, adjust your eyes. All right, so what we're going to do, I'm going to take you through step by step exactly what I want to see in this process. So we've got C2H4. First thing you're going to figure out, well, we got to figure out what our Lewis structure is going to look like. First thing, Lewis structure. Well, you know, all right, I'm sure all of you can probably figure out right away. Carbon, your Lewis structure. Is that correct? All of you can do FE, right? Right, this is FE. You all knew how to do this really quick, right? Just from organic chemistry, you should have been able to do it easily. Now, that's your simple Lewis structure. Then what you need to do, the next, in all the ones that we did, you did your Lewis structure. Then what did I expect you to do? Show me what?
The energy level diagram.
Energy level diagram. All right, so if we look at hydrogen, hydrogen is only going to be one thing. Hydrogen only has an s orbital available for a direct overlap. That's it, has nothing else. You don't have to worry about that. Then, now we got to deal with carbon. Now the thing is with carbon, it's got 2s and then 2p here. And you know that carbon and ground state looks like this. Correct? Now, all of you are gonna say, well, carbon, what is its hybrid? Will the hybrid be that it'll form? And all of you are gonna say, oh, that's easy. Carbon, because carbon's fault why this orbital hybridization has to happen. So, what is gonna be the hybrid orbital? What's gonna happen here? What's gonna happen? Cole, what's gonna happen?
The electron from the S is going to go fill the final p orbital to make sp3 hybrid orbitals.
Okay, so Cole says these are all gonna be sp3 orbitals. Okay, now, there's an issue here. Okay, because you're saying carbon is going to form sp3, 1, 2, 3, 4. Fine, the problem is that sp3, what's the shape of an sp3? What is it, Jessica? It's tetrahedral. Is this tetrahedral? No. What shape is this? What is it, Kyle? You said it.
Trigonal planar.
Trigonal planar.
Oh, duh.
All right, carbon formed a trigonal planar, which means it's not sp3. So carbon, although it does do this, it distributes its electrons. So this is the added thing. When you do a Lewis dot structure and you see this happen, if you have a multiple bond, it has to form what is trigonal planar forms what type of hybrid? sp2. So it has sp2, 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 and then it leaves. So this is sp2, 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 and it leaves a p alone. So it hybridizes in this way, where 3 of the 4 hybrids are sp2 and 1 is p. Because of the shape that it forms. Okay. Yes, Lucy?
Would they all be the same, or would the
We're gonna get to that. Okay, now, why does this happen? Well, if you were to draw, now we're gonna draw the lobes, okay? We have carbon and carbon, hydrogen here, hydrogen here, hydrogen here, and hydrogen here. Now, you know that this carbon is going to create that sp2 lobe, and then hydrogen is that circle. Right? You know that this is going to be another sp2 lobe, and then that would be that. This is another sp2. That. This is another sp2, and that. Okay. So, if you're looking at this carbon alone, it created sp2, sp2, sp2. 3 of the sp2s are done in a trigonal planar format. This carbon does the same thing. sp2, sp2, sp2. Okay. So if we were going to go through, then we have to say, okay, well, this overlap, it's a sigma overlap. And what do we call this? What are you going to call this overlap? What is the overlap called? What is Jasmine?
sp2, sp2.
This one?
Oh, just sp.
The overlap. You've got hydrogen overlapping with carbons, one of carbon's hybrids. So this is hydrogen.
sp2.
Exactly. Okay, so this is going to be an S-sp2. This is what? This is S-sp2 as well. This over here, sp2-s. This one here, sp2-s as well. Okay? This though, what is this overlap for carbon? What is it, Mitchell?
SP2-SP2.
sp2-sp2 because that is what carbon did. So carbon looks like this. So you have the three sp2s in a trigonal planar. That's what you know. Now, all right. So now that we've taken 1, 2, 3 of each of carbon's bonds, then we have to talk about the double bond. The double bond comes from because for the p orbital, your Lewis structure already dictated that it has to be trigonal planar around the carbon. So what happens with the p orbitals is that it takes the p dumbbell. Where is it going to be? Well, it's got this and this. So it doesn't matter if it was X, Y, or Z. Who cares? But it goes up and down. This carbon also has the same orientation. So, if that's the case, remember, one carbon has a p orbital available. The other carbon also has a p orbital available with one electron in it. This PP. Okay, but it's a PP indirect overlap. They are not overlapping at all. They are in conjunction, sort of like Melissa and Jasmine. They're sitting together. They have a joint effort. They're in close proximity. They're so close that there is a P indirect overlap. But we don't have to write indirect because we call this a pi bond. So just by saying pi, you automatically know it's an indirect overlap. So what we are missing to show that it's a direct overlap, you have to write what? To show a direct overlap. Sigma. So you have to do sigma, sigma. And yes, you're gonna have to do it over and over and over again.
What is the sigma sign?
How do you draw that? Like a triangle line?
Sigma is,
Oh.
Those are good ones.
I know, I did a crappy job. So, 10 marks. I give you a molecule, Lewis dot structure, energy level diagrams at ground state, hybrid orbital. Create, this is called molecular orbital hybridization. Draw your structure indicating direct and indirect overlaps, as well as drawing your bonds. Okay, all right. What happens? Are we good? This is fun. Avery, you like this stuff. All right. Let's do C2H2. Yes, we see. Because it's assuming you know it's in the secondary level. All right, quick. Lewis structure, C2H2. All of you know should be able to tell me what's going to happen, Alex.
H dot 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 dot.
So triple bond.
Yeah. And then C dot dot.
Okay, good. Good. All right, that's done. 2 marks there. Hydrogen. Yes, you have to tell me. You can't not tell me about hydrogen. Okay, because there's going to be 1 mark for that. Now, what is carbon going to do? So, be very careful here. So, look. Think very carefully. What shape has it formed around the carbons and its arms? What is it going to do with its hybrid orbital in order to make that shape happen. Gavin, you know,
SP. It's been point two SP, right?
beautiful. So proud of you. Fantastic. Gavin says you gotta create 2 of the SP orbitals, because that's linear. It's a linear form, so you have SP, what are these gonna be? So you have that. Beautiful. Then, let's draw it. All right, so we have carbon, hydrogen, hydrogen. What's this overlap? What is it, Kyle?
SP dash SP.
Yeah, SP. That takes care of one of them. This one is what? What is it gonna be? All of you, tell me.
S dash SP.
S dash SP, sigma, sigma. This is gonna be
SP dash S.
dash S,
Sigma.
this is sigma. Okay, now, how are we going to figure out what to do with the double and the triple? Suggestions. How do we show a double and a triple? Anybody have an idea? Come on,
Do you mean the
you
drawing?
guys are supposed to be the smart class.
First the drawing or the name?
Draw it. What are we gonna do? Lucy, what are we gonna do? Yes, exactly. Lucy said, just, choose PX and PY, or PY and PZ, or PX and PZ. Doesn't matter. That's when you have to use colors. This is your PX. You also have and your X one. All right, so this is the pink. Then you have the blue, which has an indirect overlap. So this is going to be called P indirect overlap. What did I put? Pi. Right? This is also a P overlap, which is also another pi bond. Okay? So this is how orbitals hybridize. This is how molecules rearrange their electrons so that they can actually form a molecule. Where do we share these electrons? How does it do it? It starts to utilize the wave mechanical model. No longer are we using Bohr-Rutherford, despite the fact we have to use Lewis dot structures to sort of give you that same basic shape. All right, so then we move to this form. There are a whole bunch of Calgary students utilizing my PowerPoint, my Google Slides and PowerPoints right now, because my niece is learning this stuff and she's dying. And she goes, I don't get any of this. So I just had to FaceTime her and I showed her, okay, here, I just sent you a Google slide, let's go through it. She goes, oh, this is so much easier now. She goes, I have to draw a Lewis structure. I said, yes. How else are you supposed to do it? She goes, my teacher just said, just do it. I said, no. Okay, so you have to go through the steps. Always start with the Lewis structure, then move through and try to figure out what you're going to do. So what I'd like you guys to do, the sheet I gave you, I want you to try, and I know on the Google side, I gave you a whole bunch of things to do. Every single one of these molecules down here, I want you to do all of them. Okay? Be able to do them. Work through it slowly, and I'm sure you're gonna use a lot of paper. But if you put it into practice that you're doing it in the right format over and over again, then you're not going to forget when it comes down to the quiz. Your quiz is going to be a 15 to 20 mark quiz. I'm expecting everything from start to finish. So if you leave out putting one as orbital, then you're going to get a mark taken off. Yeah.
What's the format of the quiz? Is it like we put a
Exactly like this. You pull one out.
Pull one out and do
So if
that?
you get an easy one like HCN, more power to you. But if you get a failure of the octet rule, like, yeah, it could be pretty miserable. Okay?
I love it.
Okay, so I'm gonna stop there. I want you guys to try to work through them. Call me over and help you, all right?
I got an easy one.
Use colors, especially with the PP overlaps that you're gonna have to be able to do. Okay?
I got
Cut that off.